Severoxan confirmați actually English. Please confirm if you can see this, if you can hear this. Just let me know in the chat, please. All right. I'll wait a few minutes to have everybody online, then I'll start. All right. Let's get going. So today we're gonna start talking about communication between processes. And before we do that, I would like to have a quick summary of what we've been doing until now and then sort of build up to why we need this communication between processes. So it all started with hardware being powerful and providing multiple computing units, and us wanting to actually use as much as that as possible. And this led to writing concurrent programs. And the first mechanism that we're using for this is processes. Now, this is not necessarily the most popular nor the most used mechanism, but it's a good starting point. Uh, and for processes, we have learned about fork. So to create a new process, you call fork, and fork has this interesting behavior where it actually duplicates the current process. It creates a clone, and that clone is called a child process, and the current process that's creating it is the parent. Uh, so that's fork. And then we learned about wait, which gets the exit status of the child process and stops its zombie state. We also learned about exec, which is used to run a program from an existing process. And exec also has a peculiar behavior. It actually replaces all the code in the current process with the code of the program that it has to run. Okay, so this is what we've done until now. We also know how to differentiate between code in the parent process versus the code in the child process based on the return value of fork. So with this, we can do a pretty reasonable concurrent computation. But there are situations where you would like to actually communicate between processes and send values back and forth so that sort of aggregate such a concurrent or parallel computation. So let's start with an example, which is not really the focus of today's class, but it's an interesting approach that will probably clarify the need for you. Let me see where I am. So let's start a Scratch file. And let's talk about adding numbers in parallel. So suppose we have a billion numbers and we want to add them, right? Calculate the sum. That's going to be rather simple. You can just have a code that looks like this. Right? And then you just say here sum plus equal, I don't know, let's say the array is called A. Okay, so this is a very simple code and it calculates the sum of a billion numbers, but it also takes a billion steps. So its complexity is O(n). Now, since we have a lot of cores, maybe we can do this faster. Maybe we can split this computation across multiple processes, and then many things can get done simultaneously. Just as a parenthesis, you can do this using, well, recently, or maybe not necessarily that recently, but you can do this using the GPU on the graphics cards, especially if you have dedicated graphics cards. That will give you really good performance, but you have to go through the pain of learning how to work with the with the CPU, which is not so bad unless you really try to get performance out of it. But today's blockchain and Bitcoin things, all that mining is going on GPUs because they're really good at this kind of calculations. So I just wanted to explain to you really quickly how you would add a lot of numbers in parallel so that you get the idea, and then we'll try to do this with just a few numbers. So here is the general idea. Suppose we have an array of 16 ints, okay? So no more than that. Oh, sorry. Right, these are the indexes. And then the numbers in the array are 100, 101, 102, 103, 104, 105. Takes a little bit to get this written, but right, so those are the numbers. So instead of having a simple for cycle that just iterates through everything and adds, what if we create 8 processes? Right now, this is a forced example. Nobody would do this for 16 numbers, and nobody would probably do this for a billion numbers. They will probably use threads. But for the sake of the argument and as a foundation for the next piece, let's consider that we are creating 8 processes to add these 16 numbers. And the first process will add position 1 to position 0. So on position 0, we will have 201. The second process will add the third to the second, so that will be a 205. The third process will add the fifth to the fourth, so that will be a 209. The fourth process will add 7 to 6, so that will be 213. The fifth one adds the ninth to the eighth, so that's a 217. And then the sixth one adds 11th to 10th, so that's 221. And then the seventh process adds 13th to 12th, so that's 225. And finally, the eighth process adds the last to the penultimate, and that's 229, right? So at this point, 4 processes stop, and the remaining processes continue in the same way. So the first of them adds 2 to 0, so that will be a 406, right? The second one will add 6 to 4, so that will be a 422. The third one adds 10 to 8th, and that's a 238, I think. And then the last one adds 14th to 12, and that's a 254. Hopefully I'm not messing up the additions. All right. At this point, two of these processes stop. The remaining two go on in the same way. The first one adds fourth to 0, and it's an 828. And the second one adds the 12th to the 8th, and it's a 4. Oh, something is wrong here. Yeah. This is 4. Numbers were a little too small. All right. And now we have here a 892 maybe, something like that. Right? And then one of the two stops, and then the last process just adds these last two numbers. And then we'll have here 1. Oops. I'm using the keypad and Putty is acting up. So this would be the final result. All right. So the trick here is that we added 16 numbers in 1, 2, 3, 4 steps. We could add in this way, we could add 1,000 numbers in 10 steps or 1,000,000 numbers in 20 steps. or a billion in 30. So as long as we have a lot of computation units, this can go really fast. It's an O log n performance. It's a really good thing to do. You don't have to cycle a billion times. You don't have a billion moments in time that you have to wait for. They will be simultaneous, and the result comes much faster. So if you get this idea, um, and a colleague of yours from the Romanian section said, this looks like divide et impera, and it does, except that the divide et impera that you have been playing with in algorithms said something like solve this subproblem, then solve the other subproblem, and then combine the results. In this case, it's the same thing, but there is no then. It's solve this subproblem and simultaneously solve this subproblem, then combine the results, right? So the trick here is the combining the results, because we solve those problems simultaneously, concurrently, in separate processes. So let's try to do this using processes, and let's move our attention to the class notes. Basically, we're going to do it with only 4 numbers, okay? So we will initially have 2 processes, parent and child. Parent does this addition, child does this addition, and then parent adds this to this, and we're done. So let's see how this is happening. Obviously, this is the first example. It's very heavy for what it has to do, but the point is to get the idea. So we have this array. We create the child process with fork. The child processes adds third position to the second, and it ends. The parent process adds the first 2 positions, right? Position 1 to 0, and then it waits for the child to finish. Now, once the child finished, parent adds the second position to position 0, and then prints the result. Now, this may seem all good to you, and I will implement it, but if you read closely the text above, you will see that the result is not what it should be. It's actually much less. It's 6 instead of 10. So let's just see this happen. I just need to add here a bunch of include statements first, and then so I think we need std lib, we need uni std, I think, and then because we're using wait, sys types, and then I think sys wait. All right, so let's compile this. Actually, yeah. All right, so we're good. And when we run it, the result is 6. So reading the material, you probably saw why. The answer is really simple. You have 2 processes. The child process is a clone of the parent. And when I say a clone, it's practically the whole memory of the parent gets duplicated in the child. So when the child does this addition, it does it in its area of memory, not in the parent's. And because there is no transfer between the two, each of them is with its own memory, practically when the parent gets to do this, A2 will be still 3 in the parent, not 7 as in the child, because the child modified its own A of 2 and then it stopped. So that value is lost. Consequently, we're missing 4 from the final result, so that's why it's 6. So this is the point where aggregating these results that you have done concurrently requires some way of communication. So the communication mechanism is called pipe, and not it's not a coincidence that it has the same name as the pipe that we're using in Bash. In fact, the pipe we're using in Bash is named after this. So let's see how these pipes are used to communicate between processes. And we're just going to take this code, right? And then we're going to go through this list of things which contain, it's not that long, but there are lots of details that have lots of consequences. So let's copy this into b.c and just modify the program by adding pipe to it. And I'm going to keep the code right here so that you can look at it ahead of time. But the story goes like this. I need some mechanism to transfer data from the child process to the parent. This mechanism is called pipe. And the pipe is really a buffer in memory, in kernel. So you need to create a pipe, and then you have to have the child write the value to it and the parent read it from it. Now, when you create a pipe, the pipe is automatically opened at two ends, one end for writing and one end for reading. So you're getting back two ints. Just like open, when it opens a file, it returns an int, and that's a file descriptor. That's exactly how pipe is treated as a file, but it's as if a file opened twice, once for writing and once for reading. So let's declare here an array of two ints, which will contain these descriptors, and then we create the pipe just like this. That's it. So with this, we have created a pipe. And in P, when this call is done, P will contain two numbers, and the first number is the file descriptor for reading from the pipe, and the second number is the file descriptor for writing into the pipe. So we have the pipe. Now, you will notice that the code here has a lot of close statements, and I will get to those. They're essential, but they are a little, they kind of are not about the main logic that we wanted to work on, meaning sending data from one place to another. So to send data, you just need to have at this point, the child write data to the pipe. What I need to tell you is that the parent created the pipe, and then through fork, the child inherited the pipe ends. So now the pipe is in the kernel, and both the parent and the child have each of them two ends for working with the pipe. So the child will simply write to the pipe the value of A2. All right? And the parent, once it's done its addition, will read from the pipe using the reading end. You see, the child wrote using the writing end. Now the parent reads using the reading end, and is going to read in the same position, AF2, size of int, and that's it. So at this point, the value from the child is in the parent, and when the parent does this addition, it will actually lead to a final result of 10. But we need to close pipes. So this matter is really important. You might be used to ignoring these details. You don't really need to close the file because it will get closed when the process stops, right? Or you don't need to free memory because it will get freed when the process stops. But in this case, if you do not respect the rules that I'm going to tell you with close, you may end up with programs that get stuck forever. So let's see, we have a water addict asking, what if read is executed before write? Okay, so this is a very good question. So your colleague's question is, what if the parent tries to read before the child writes? This is very likely. However, this is your answer, and I'll get to it. So just wait a second to to go through what I've got here. Let me just resize this properly, and then I'll clarify this. Basically, pipes behave very much like synchronization mechanisms as well. All right, so coming back to closing, you need to close. The rule is close pipe ends as soon as possible. As soon as they're not needed anymore, close them. If you don't do that, your program may get stuck because of the same behaviors that I told your colleague are the answer to his question. So these behaviors that make sure that even though we may try to read before writing, we're still fine. This behavior may lock up your programs unless you close as soon as possible every pipe end. So here, for instance, the child does not use the reading end. The child only writes to the parent. It doesn't use the reading end, so we close it as soon as possible. And this is the earliest moment we can close it in the child. The writing end can be closed right here as soon as we are done writing. So close P of 1. The parent doesn't use the writing end. The parent only reads. So the parent, where should the parent close the pipe, the reading end of the pipe? And basically, this is the earliest moment where it can do it. Close P of 0. Sorry, P of 1, the writing end. And then as soon as it's done reading, it can also close the reading end. So this is the whole code. It has three, let's say, areas. Create the pipe, read right from the pipe, and make sure you close the ends as soon as possible, each one of them. So if we compile and run this, the final result will be 10. So let's look again at the code and see if we have questions. Can't we close right after we create the pipe? Thank you, Berzent. That's the question I wanted to hear. The answer is no. If I close, so what Berzent is asking is, what if we take this from here and we move it here, right? Or he's actually saying, what if we don't move it here? If you do that there, then the child and the child will inherit P1 closed. Exactly. If you move it under the fork, this line is executed by both parent and child, so child will close its own P of 1 too early. Only here can it close it. Consequently, the earliest place where only the parent closes this is here. Cool. So we clarified this. So now this is how you communicate through pipe. As a summary, the pipe must be created by not necessarily by the parent. The pipe is inherited. Okay? Actually, not even the pipe. The pipe ends are inherited by child processes. So even if this child process creates a child of its own, it will still inherit the pipe ends. So the way to communicate through pipe is you have to have someone upper in the hierarchy, some ancestor that creates the pipe. And then you inherit it and you can write. Okay. Marin is asking, what if we wait for the child before reading from the pipe? It will get stuck. I'll get to it, Marin. Why do we write at P1 and read from P0? That's how this is designed. The pipe is like a file, but it's actually a buffer in memory, and it's opened twice. You open it once for reading and once for writing, and not you. The system does it for you, and you just get back two descriptors. One descriptor, P of 0, is used for reading, and P of 1 for writing. You don't open a pipe for read and write. You only open it for one of the two. So you open it twice if you want to do both. In a way, it's the same idea as standard input and output, but these are just indexes in this array. But yes, the idea is similar. Now let's have a look at the special behavior of these things. Okay, let's look through all this text that it's written up here and see what we need to do about it. So first of all, yeah, the pipe is a buffer in memory, opened like a file twice, once for reading, once for writing. We've done this. Okay, this opening is done automatically for you when you create it. So pipe not only creates it, but also opens it. And 0 for reading, 1 for writing. This is clear. Now this piece is the biggest one. This special behaviors have side effects. So there is a lot to talk about. Okay, so mortuary, I'm not really sure how to answer it. You just open it. You don't. You just create it and it comes open. And you make sure you read the same and you write to it and make sure you read the same way. Well, you write to it, but I'm not sure what you mean by reading the same way. So maybe you can rephrase the question to be more specific. Right. Well, while he does that, I'll continue with the special behaviors. So here we go. Uh, in Unix, most of the things are treated as a file. Oh, I got it, Marjorie. Thank you. How would you open a pipe for strings or pointers? What does that mean? Open a pipe for strings or pointers. You don't open pipe for strings nor pointers. You open pipe for data. You write bytes into a pipe. The fact that you have p of 2, which are two ints, those are just the file descriptors, and you write in them anything you want. If you're thinking of this, well, you can always wrap the pipe end in a file and then file pointer, and then you can use fread and fwrite and put strings there. But you don't really need it. It's enough to use it in binary way, just putting bytes there. Okay. So where was I? All right. So special behaviors. And I was saying that in Unix, most everything is a file. Basically, uh, you work with files using open read write, right? You work with devices, be it a mouse, a joystick, a sensor. It's still gonna be the same API, open read write. Open will initialize the driver, read will get data from it, write will write data to it or configurations. So this I/O interface of Unix is really nicely designed, and you are using the same the same API. Now, when you use read and write with pipes instead of regular files, things are a little different. And the rules here will take you through those. Let me see what Steph is asking. Is there a fixed capacity for what we can? Yes, pipes are not infinite, so there is a limit to it. You'll have to search what's the maximum pipe size, but normally you're not gonna transfer huge amounts of data through them. You can, but you'll need to figure out the capacity, and you can also increase that upon necessity. So yes, you can work on that if you need to. Normally you shouldn't. So special behaviors. First thing is when you work with the file, read and write have a way of working. Read just consults the data and gives you back what it found, but leaves the data in place. When you work with the pipe, read actually removes the data from the pipe. It extracts it. It consumes it. When you write to a file, write can simply overwrite what is there. Right? But when you work with a pipe, write actually pushes data into the pipe. It produces data. It adds data to a pipe. It cannot override anything. So it's literally as if you are communicating through a pipe. And the bytes are ping pong balls, right? So writing into the pipe means adding ping pong balls in the pipe, and reading means removing those ping pong balls from the other end, right? That's how you have to visualize it. Write pushes data in, and read removes it and returns it to the user. So this is the first special behavior. It's more like a produce consume behavior rather than read write. Now the second behaviors are those that can get your program locked up. And look at them. The question is, what if I try to read from an empty pipe? And this has two parts, and you will have to assimilate them, and it's not going to be easy. So if the pipe is empty, then read is waiting for data. And it waits for data until some data comes. And I'll emphasize some data comes. But it may also stop waiting if it figures out that there is no writer left for the pipe. No writer left for the pipe means all the write ends of the pipe are closed. So if you try to read from an empty pipe, no data is coming, and you figure out there is no writing end left open, it means that nobody will ever write to the pipe anymore, so there is no point in waiting. But the behavior of read for waiting can lead to lockup. Okay, so read from an empty pipe waits until there is data or until there are no more writers. Symmetrically, write, when it tries to write in a full pipe, will behave the same. It waits for space or for no more readers, meaning all the reading ends to the pipe are closed. Questions for this? Let's see. William, is the pipe a standard EXE program? I'm not sure how to answer that. EXE kind of refers to Windows. Windows has its own way of implementing pipes, but I don't know what you mean by a standard. It's a mechanism that comes with the operating system, and you can use it in any program, yes. All right, so pipe, you could think of the pipe like a queue, yes. You could think of it like a queue. I think the queues should be double-ended by default anyway, right? Because otherwise it would be a stack. So yeah, a double-ended queue. You push in one end and you remove from the other. All right, now finally, and this may come as a surprise to you, so the first one is not read-write, but actually produce and consume. The second one is a waiting behavior, depending on the availability of what you want to do. If you want to read and there is no data, then you wait until there are no more writers, maybe. If you want to write, but there is no space, you wait until there are no more readers. And then finally, and this may come as a surprise, is read and write will not make any effort to handle as much data as you tell it. If you tell read to read 1,000 bytes, there is no guarantee that read will return 1,000 bytes. The only guarantee is that it will return some bytes, maybe, unless there is no data, but it will tell you how much it read. So you may end up saying read 1,000, and you get back from read, and read tells you I only read 15. This means that if you actually want 1,000, you have to try again to read the remaining 985. And maybe the second read will return another 30. So if you really want 1,000, you go back and you try to read the remaining 955, and so on. Now, this is a behavior that doesn't really happen with files, but when you use pipes, which is actually a communication device, you kind of cannot really expect read to sit there forever until the data that it wants arrives. You want 1,000, then it's your business to figure out how much do you want to wait for that data to arrive. Read will go. If it finds something, it brings it back. If it finds nothing, waits according to the rule, and then it comes back with something or maybe nothing, but it tells you, I read this much. And same goes for write. If you tell write to write 1,000, write will actually write as much as it can. When the pipe is filled, it comes back and it tells you, well, you wanted me to write 1,000, I only wrote 70. And then if you really want to write the rest, you have to try again. So these are rules that are actually important to know, because if you ignore them, your communication may go badly, simply because you will be reading partial data. So here I have a little story. This actually happened to me, and it's interesting to see the effect of it and how unexpected it was. So I was working on this application. It was an application that was reading data from a database, and data was confidential. It had to be encrypted to prevent, attacks. And this application would read the data from database and then decrypt it and then display it. And when the decryption would go bad, you would just see all these weird characters, Chinese-like characters in the browser. So one day, the application, after a long while actually, it wasn't from the beginning, it was working just fine. And after a few years and some upgrades, I guess, the application started to show these weird characters. The encryption was broken. So debugging, I reached the point where the application was reading the key from the file. And the key was 8 bytes, the decryption key, 8 bytes. And the code said read 8, but the code did not check if actually 8 were read. And it turns out that only 7 were read. Just like that. And then obviously an incomplete key yielded bad decryption and so on. So the solution was, all right, if it didn't return as much as I wanted, try again to read the rest. And then it all was fine. Now this key was not really read from a file, it was in Java and it was reading it from a stream. So the behavior of read in that case was kind of similar, was similar to this. And whomever wrote the code years before didn't really bother with this, but then this came to bite back as soon as the moment was ripe. And it's hard to tell when such things would happen because it's all a matter of circumstance. System is busy and heavily loaded, then things will start behaving differently than they usually have during development, and you start seeing all these other bugs. But isn't it a bad idea to use a constant instead of size of? You're kind of confusing me, William. What constant? Where would you want to use size of? We'll have to wait a few seconds for this to get to you and then for his answer to get back. I'm not really sure what you said the program. Oh, well, it was their choice. It was their choice. Whatever encryption algorithm they used, use an 8 byte key. I don't really know. The fact is that I said read 8 and it returned 7. And it's kind of unexpected. 8 bytes is not so much. You would expect them to come right away, but they didn't. So yeah, maybe it was a bad idea, but it worked fine. Okay, so these are the special behaviors. This behavior will lock up your program unless you close the pipes as soon as they can be closed. And this behavior will confuse you, but I don't think we'll have problems in this class that will actually touch on this behavior. But as soon as you start working with the network, if you do it in C or you do low-level reading, then you'll have to keep this in mind. All right, let's see the next piece. Yes, this is about behaviors B2 and C2, which can lead to program being stuck. I'll show this to you soon. And the fact that you have to close the pipe ends as soon as they're not needed anymore. Also, the fact that the pipe is inherited from parent to child, and then if you want to communicate through pipe between two processes, somebody above or one of them has to create them and the other to inherit it. All right. Next is, yeah, we talked about what would happen if you try to move this close a little higher. And then here is a piece of advice. If you want to do two-way communication between processes, use a separate pipe for each direction. The trick is, if you want to do duplex communication, A writes data to B, and then B responds to A, and A reads the response, right? Basically, as soon as A writes to B, it should start trying to read the response from B. But there are big chances that it will read back its own request because it's the same pipe. So to avoid this kind of thing that will confuse things to no end, my suggestion is use pipes, separate pipes for each communication direction. All right? So two pipes means two arrays like this, two of them. All right, and then just a warning. It's likely that you will confuse pipes with their ends. No, a pipe is a pipe, and what you get are two ends to it. You never really touch a pipe. You only work with the ends towards the pipe. So when I say close the pipe, I always mean close its ends or one of the ends, depending on the situation. All right, so let's try a more complex program. And it's going to be an eeny, meeny, miny, mo, this kind of children's counting, right? Well, we'll have three processes that will do an eeny, meeny, miny, mo, and they will talk in circle using pipes, something like this. We will have a parent process that will send, in this case, I think we start with 20. We'll send 20 to process A, which will then send a 19 to process B, which will then send 18 to the parent. Hold on, my ASCII art is not as great as it should be. Right? So B sends 18 to P, then P to A17, A to B16, and so on. And this thing just spins. We just send this number and keep decremented through pipes until it reaches 0 when everything stops. All right, this is the program that we have to do. So you have the code in, you have the code in the in the class, in the lecture notes. So let's just take it from there. Let's copy whatever we had here, b.c into ini.c. Let's delete this I just want to keep the headers. So let's delete this and then copy the program instead. All right. It's a metaphysical pipe. Yeah. I don't know how that would be. You can use pipes to think metaphysical thoughts. But how would you get your hands on a metaphysical pipe and what you'd do with it? I don't know. All right. So here is the program. So let's just have a look at it, and maybe it's easier to see it if we make this wider and see the whole thing in one shot. Something like this. All right. So what do we have here? We will have a parent that will have two child processes. parent will send to A to B, B back to the parent. So we define 3 pipes. And we name them accordingly, P to A to B, and B to P. And we also have this N, which is the number that we keep sending and decrement it. In the parent, we initialize all the pipes. So then they will be inherited by the children. Then we create process A, which does a trick. We create process B, which also does a trick. And then we have the parent doing the rest. And we'll start with the parent because the parent initiates the play. So we have 3 pipes, which means 6 hands, and we have to close everything that we don't need as soon as possible. So in the case of the parent, and you'll see also the children doing this close, lots of closing going on. In the case of the parent writes to A and reads from B. So since it writes to A, it closes the writing to A because it doesn't need it. Since it reads from B, it closes the writing to B because it doesn't need it. And it also closes the A to B because it has nothing to do with that pipe. So we close all these 4 ends that we don't use. Initialize N to 0, and then we start the play by writing in this pipe, which goes to A, the value of N, 20. And then the parent starts reading data from B, from this pipe, from the reading end of B to P. If the read returns something less than 0, it means that the pipe either was closed or there is no more writer to give data, so we have to stop. The game is over. If the value that was read, n, is less or equal to 0, then the game is over because that's the rule. We keep decrementing till we reach 0, so we stop, we break. Otherwise, we print out, I'm the parent, I got this much, and I'm sending this much, meaning I got n, and I'm sending on n minus 1. Then we decrement n, and we write n to PA. At this point, process A, having closed its own unnecessary pipes, tries to read from the parent. As soon as it gets something from the parent, announces it, decrements it, sends it to B. As soon as B gets something, decrements it, sends it to the parent. As soon as the parent gets something, decrements it, sends it to A, and so on. It just goes round and round. When they are done, they close the remaining pipes, the ones that they used, and then they exit. So let's compile this program and see it running. All right, so ini, this is it. Basically,